So now we are on chapter 3, section 5. We're talking about moles. So moles are what chemists used whenever they are counting atoms. They're using that as a unit. So you're going to have a whole bunch of atoms in a mole. So you can think of that term mole kind of the way you think of, just for example, like a dozen for a dozen eggs, or a dozen donuts. So the number of eggs in one dozen is 12. All right, so, but if each egg weighs 60 grams, we could determine how many eggs are present in that carton by closing the carton and weighing it, right? If we know how much one egg weighs, right? So you can do this similarly for the elements on the periodic table. You can also think about this sort of like M&Ms in a bag, right? What I mean by that is that we have, let's say, a bag of M&Ms. So if you have a big bag of M&Ms, you've got a bag of M&Ms, and let's say you weigh one of them, right? Because maybe the egg example didn't do it for you. Let's say you get the mass of one M&M, but you want to know how many M&Ms are in that bag. Well, what's something that you could do? So you could just weigh one of those M&Ms rather than count all of the M&Ms. That would take a while. And you could then get the weight after you weigh one M&M of the bag. And you can use a conversion or dimensional analysis to figure out how many M&Ms are in the bag. For example, let's say you had, I don't know, a 357 gram bag of M&Ms. All right. And you know that one M&M, let's say, weighs how many grams? Maybe 0.00 or 0.800 grams. All right, so you'd be able to cancel out those grams, and then you could figure out the number of M&Ms. All right, but some of the M&Ms might have a little bit different of a mass, right? So that is actually very similar to elements. Whereas elements, you'll have isotopes that have slightly different masses amongst atoms of that element, right? Okay, so I think that's a pretty good example. So you can think of that in kind of interchangeably. So basically, we can replace M&Ms. M&Ms are my favorite, so that's why they're a good example for me. But we can think of this in terms of an element. All right, so if we have carbon, right? Carbon is so famous. Carbon started it all. So we think of carbon on the periodic table. So basically, if we have 12 grams, all right, of carbon, we want to know how many atoms are there, but atoms are so small, all right? We don't want to count all of them. So that's why we use this unit, mole. So there's a whole bunch of these atoms in a mole, all right? But we can use our mass. We can use our mass to help us figure this out, all right? So basically, let's see, we have 12 grams of carbon, and we have let's say in one atom of carbon, we have, how many grams would one weigh? So we know this, all right? So there's a scientist who came up with an equation to help us better understand what's in a mole, or how we can relay this in an easier way than counting individual atoms. So basically, this number that we're going to get from this equation is going to be 6.20 times 10 to the 23rd things. Okay. And the reason I say things is this is an important number that we're going to use to account for a lot in this lesson. And we use this number a lot in chemistry. It's a magic number. It's a very special number because, so this is going to be the number of, all right, so we can use this to figure out the number of carbon atoms in 12 grams. 12 grams isn't very much. That's about the size of a AAA battery. All right. So you have this many carbon atoms and 12 grams of carbon. If you have like a bag of carbon, like the bag of M&Ms. All right. So this is a special number. We use this number that we get from carbon, and we apply it in lots of ways, and it has a special name. All right. So this is how we know what a mole is. This is how a mole is defined. In this case, this is a mole of carbon atoms. A mole of carbon atoms. All right. And now we're going to talk a little bit more about that number. All right. So, and we're kind of changing gears. So you noticed that to do that math, we had to know the mass, the average atomic mass for that element. All right. So 1 mole of any element has a molar mass in grams that's going to be equal to the atomic mass of that element. So we can use that information on the periodic table here. So the mass tells us the mass of 1 mole of a substance, okay, it corresponds to the mass of a single atom in atomic mass units. All right. So we just did that math. I just showed you how it was obtained. I told you this number is going to come up a lot. You're going to need to know this number, okay? And it has a special name. I'm getting to it. And if I keep repeating it over and over again, that's good because you're going to remember it. So this is 602 hexatrillion atoms, right? And that's a mole. All right. And so basically when you're considering what molar mass is, the mass of a mole, the atomic mass is going to matter, right? Because the mole is made of atoms. That's all this slide is trying to tell you, basically. All right. So the number of atoms in a mole is better represented in scientific notation because this is a giant number and nobody really wants to use numbers that are so big. All right, so you can write that out as 602 times 10 to the 23rd. All right. And that number is called Avogadro's number. Some of you might already remember. So the person who did the work to figure this out so that we can use moles instead of doing this in a much more cumbersome way was an Italian physicist named Amedeo Avogadro. So it's named after him. It's almost like avocado, but it's Avogadro. Okay. So basically 6.02 times 10 to the 23rd atoms in atoms equal 1 mole. All right. Yes. Okay. So, and if you look here, this is going to help you to understand that every element is going to have, every element, has a different mass for those atoms. Just like, so a dozen eggs and a dozen bowling balls have different masses, right? A mole of silver, like right here, is going to have a different mass, or a molar mass than carbon atoms, right? So you can see that. basically, you're going to have, as you have a larger atomic mass number, you're going to have a larger molar mass. All right, it makes sense. Okay. So larger atomic number, you're going to have a larger molar mass. All right. And we're going to do some math to figure moles and atoms and molar mass. And to do all this, first, and this is how I've always done this from the start, right? Whenever we did the math counts, determine the unit of your final answer. And a lot of times, you know, I've written that as the very first thing, so I don't forget my units, okay? Or don't get them wrong. Then you're going to establish the given information. So this is, remember, what do I need? What do I need? What do I have? Decide how to set up the problem. So that's when you're connecting the dots. Solve the problem. Check your work so that you don't make any mistakes. No rushes. Take your time. Get the right answer. It seems difficult, but you can do it. All right, so the formula weight for a compound is going to depend on several different atomic masses, right? You're going to add that together. So we're going to do some examples. No worries. All right. So the molar mass of the compound is going to be equal to the formula weight with units of grams per mole. Okay. And also, eventually, especially whenever we're getting into biochemistry and we're talking about the weights of proteins, we're going to be using another unit called the Dalton. I love that word because it happens to be my nephew's name. All right, so that's the same as the atomic mass unit. All right, so Dalton atoms. It's my last name and it's my nephew's first name. It's an easy way for me to remember that. Maybe it'll work for you, but maybe not. So let's work a couple of problems while it's still fresh in our mind. We're just gonna cement it, work some of those problems now. That's not the one that I want. This is the one. All right. So section 3.5, the mole. All right. So we're going to do 3.37 first. Okay. So 3.37. We're going to compare the number of atoms and the number of grams present in 1 mole of silver and 1 mole of gold. All right. I'll do silver and you can keep gold as a practice because you have this in your textbook. All right. All right, so let's do A. All right, the number of atoms and grams. All right, so we want atoms and grams. All right. So you can circle that and write gold. All right, gold. All right, in 1 mole of silver. So we know at the end, at least of one of these, we want atoms. All right, so I'm going to put that there. We want atoms, and it helps you to write silver. That way you don't get confused and mixed up. All right, so I'm going to show you what we can do. All right, we want atoms, and we have moles. If we have moles and we want atoms, well, what can we use? We can use Avogadro's number. You know, thank goodness for Avogadro. So you have 1 mole of Ag, which is silver. All right. So you can multiply by Avogadro's number because in each mole of silver, you're going to have this many atoms. Per mole, this many atoms times 10 to the 23rd. All right. And that's in moles Ag. And so, you know, I should keep my units here. All right, so this cancels out and you get what? What's 1 times 1? This one's really easy. 6.0 times 10 to the 23rd. That's why I know y'all can do B, right? So it's also 1 mole. All right. So y'all are going to get what happens there, right? It's the same number of atoms, in the moles of the elements, right, on the periodic table, okay? So now we've done one of our things, so we can check off atoms, right? And you can write on your exam like that. Put goal, check it off if you did it, all right? And reason out, why is this the right answer? Because I know my concepts, studied my concepts too, and fully understood them, what they mean, can explain it, all right? So now what are we gonna do? We need to get the number of grams in 1 mole of silver. All right, so we want grams. Let's write grams over here, grams silver. All right, so we have 1 mole of silver, and we know this is whenever we can use, we want grams, and we have moles. So what you can use is the average, what? The average atomic weight. So let's see, let's check out silver. I just had that here. So where is silver? 107.9. All right. So 107.9 grams silver. So that's the unit that we want. There you go. And so, and this is in 1 mole, one of those moles. All right. That's like the whole bag of silver, all right, on that element. So in one of those moles, you have this. So now you can figure out the grams in 1 mole. And of course, that's going to be 107.9 in this. All right. There you go. All right. So now we're going to move on to 3.9. 3.39, excuse me. Calculate the following. A, the number of sodium atoms in 0.250 moles of sodium. Okay, so how are we going to do this? So we want number of sodium atoms, right? So let's put that at the end. Sodium atoms. That's so funny. If I were to name my child Sodium, then their name would be Sodium Atoms. That's so silly. Anyway, all right. So we have 0.250 moles. 0.250 moles sodium. That's not what we want in our answer. We're gonna have to cancel that out. All right. So in 1 mole of sodium, it's a lot of space for the number 1. Just bear with me. You're going to have how many atoms? Well, we know that. It's going to be the magic number, Avogadro's number. All right. So you're going to cancel out moles, and you're just going to multiply across. What are you going to get? Do this on your calculator. You can pause the video if you want. Do it on your calculator. Make sure you get that. Make sure I'm right. All right. Because everybody makes mistakes. The number of moles in 4.0 grams of lead. All right. What are we going to do? We want moles lead. Go ahead and write that. Moles lead. So what are we going to do? What do we have? We have 4 grams. So can we get over to moles? We can. How can we do that? Because in 1 mole, we know what the mass is, right? If you look at your periodic table, you're going to get, okay? So if you're going to do your math, you should get 0.019 moles. So that's how many moles are going to be in 1 gram of lead. I mean, 4 grams of lead. All right. Need a little more coffee today, apparently. All right, see the number of atoms and 12.0 grams of silicon. All right. So what can we do? We have gram silicon. We want atoms. So you need to connect the dots. So we know what we want. we want atoms, silicon. We want silicon atoms. So we know we're going to use Avogadro's number, right? This is going to be a little bit bigger problem. Atom silicon. All right. So what can we do? We can have, we know, all right, so we have 12.0 grams of silicon. We have that. And we're going to want to cancel out grams of silicon. So we know that in that bag of silicon from the periodic table, that's going to be 1 mole. All right, so we can cancel out grams and we can get over to moles. And then from moles, we can get to atoms, because for each one of those moles, we're going to have 602 times 10 to the 23rd atoms. All right. So the mole is the big thing, and the atoms, they fall under that category. There are many atoms in that mole. All right. How many? This many. All right. So, all right. And you're going to cancel out moles, because in 1 mole of silicon, that's the number of atoms. So you can do your math and you should get 2.57 times 10 to the 23rd. Make sure I do my calculator math right. All right. Cool. See, if I can do it, you can do it. You can. Nothing special about me. Y'all can definitely do this. See how easy that was? All right. 3.41. All right. Let's see. What are we going to do? All right. Determine the molar mass of the following compounds. So how about I do a couple of these and then you do the other one? Like maybe I could do A and C. If it doesn't matter. They're all going to work the same way, which is why I know you're capable of doing one on your own. And everyone wanted extra practice problems. So there you go. All right, calcium sulfate. So how are we going to write that? All right. So what have we got? We've got 1 calcium, 1 sulfur, and 4 oxygen. So how are we going to figure out the mass? Well, it's going to be the sum, right? So how are we going to figure out the molar mass? We've got to get the sum here. Okay, so we know we have 1 sulfur is going to be, or calcium. Let's do calcium first. 1 calcium, 40.8. It's going to be 40.08. Then you're going to add that to 1 for sulfur. It's going to be about 32. And then 4 oxygen. You're going to use oxygen so much, you're really just going to know, you're going to know what the average atomic mass number is going to be after a while. And so if you do this math, so that's multiplication right there, all right? Because of the number of oxygen atoms you have here. So that's 4 oxygen atoms. That's the atomic mass on the periodic table. You're going to get 136.15. And I told you that's grams per mole. It's on the slide. All right. So you're going to have to know that. You have to know. So I'm going to do C, and then you can try B, and you can check the answer in the back of your book. All right. And if you can't get it, let me know. I'll do that one in class. You can make sure you got it right. All right. So hydrogen peroxide. All right. So you can write like hydrogen peroxide. You can use that on wounds as a germicide, or I don't like the word germ, just antimicrobial, or you can whiten your teeth with that. You can swish around diluted hydrogen peroxide and whiten your teeth. You can do it. I've done it before. So 2 what? Hydrogen. So we're going to want grams per mole hydrogen peroxide. So we have 2 hydrogens. So that's going to be what? That's 1.008 all the way at the top left of the periodic table. You have 2 oxygen, all right, 2 oxygen, and I think that's it, right? So what's that going to give you? 34.02. All right, you guys can do B. Let's see. And I think here's our last problem, and then we'll go on to the next section. 3.43, determine the number of molecules in a 325 milligram dose of aspirin. All right, this is the molecular formula for aspirin. Okay, so how are we going to do it? We want the number of molecules. All right, so we're going to be using Avogadro's number. All right, so how are we going to figure this out? So we have to know first, what are we going to want at the end? How many molecules of aspirin? C9H8O4 is aspirin. All right. What are we going to do? This is going to be a bigger problem, I can tell. So we're going to do like this. All right. So we know we're starting, we have 325 milligrams of aspirin. All right. So, or you can write it out. That's better. All right. And you're going to want to convert over to grams, because this whole time, what unit have I been using? Grams. That's what sort of conversion factors we have here, right? So in 1 gram, you already know how to do this. You have 1,000 milligrams. So milligrams are going to cancel out. Now we're in grams, but we want to get over to molecules. So what are we going to do? So in 1 molecule of C9H8O4, we're going to have a total mass number, all right? So how are we going to figure that out? Well, we just did that, all right? So we're going to have 9 of carbon, and we're going to have 8 of oxygen, 1.008, right? And we're going to have 4, oxygen is going to be 16. You're going to get 180.154 grams. Okay, then you're going to want molecules, so you're going over with Avogadro's number. All right, so that's 6.02 times 10 to the 23rd, your magic number. So that's molecules in 1 mole. And your answer is going to be 1.09 times 10 to the power of 21. It's a lot of molecules. Glad we have Avogadro's number. All right, so now let's go over to 3.6. So now we're talking about covalent compounds as far as shape goes, because before we were talking about 2 dimensions and we were just talking about Lewis structures and so forth and naming, but we didn't have 3-dimensionality accounted for yet, did we? So that's what we're going to talk about now. So here is a Lewis structure for methane, all right, CH4. We have our carbon and we have these double bonds to hydrogen and everybody's happy, right? So on flat paper, you're going to have 90-degree angles, all right? And if the electrons are really in a 3-dimensional space, something is going to happen. There is going to be some repulsion there, all right? So those electrons are almost like siblings. They're going to want to be farther away from each other. They don't want to be by you. So they're going to be as far away from each other as they can be. So in this shape, which is called a tetrahedral, and we're going to talk about that, the angle that you're going to have with the space that's going to occur between all of these bonds between electrons is going to be 109.5 degrees. That's what's going to happen in a tetrahedral. Okay, so here in carbon, you need to know something. We need to know that there are areas of electron density. So these are the areas of electron density, and there are 4 of them, 4 areas of electron density. All right, so when you have 4 areas of electron density, you're going to form a 3D shape that's tetrahedral. Okay, and we're going to get into a little more detail about what's happening with these electrons and how they form that shape. So when we're drawing this on paper, how are you going to make the 3D shape on paper? Well, whenever you see these lines that are straight, these are just, they're two-dimensional. They are as they are. But we're going to use wedges to indicate that the configuration would be going behind the paper, sort of, behind that plane. All right, so we use these dashes for that. And we use these wedges if really that hydrogen right here, this bond between this carbon and this hydrogen is coming out towards you in front. So that's what this dash, I mean, not this dash, that's what this filled in wedge is going to be. Dash is behind, wedge is in front. All right. And I made that really hard to see. So, all right. So those bonded pairs repel each other equally. So these are bonded pairs. All right. So if we draw that out, carbon 1, 2, 3, 4, and we have these hydrogens with 1. These are bonded pairs. All right. So bonded electrons are going to behave differently. They're going to repel each other equally as opposed to unbonded pairs of electrons. All right, so that's what we're going to get to. But the reasoning that describes this repulsion is called the valence shell electron pair repulsion model. And we know what all these words mean, right? The valence shell, so the outermost shell, the valence shell electron pairs repulsion model. All right, they repel away from each other. Okay, so this is what's happening. This is what's happening with methane. Okay, so really you're going to have like carbon there, and you're going to have, there's going to really be some dimensionality to this. Okay, it's really not as flat as it seems when you're learning the structures, right? So you're going to also have, like I just mentioned, you're going to have non-bonding electrons. So you're going to, whenever you're thinking about the geometry of these molecules, you're going to have to know that there are these charge clouds that happen. All right, so you have charge clouds with bonding electrons, and you have charge clouds with non-bonding electrons. And the non-bonding electrons, those electrons, they're just stretching out there, repelling everybody as far away as they can. All right, so that's going to make the structure also different in a way. If you have that non-bonding pair of electrons that don't bond with another atom. Okay, so I'll show you what I mean. All right. So here we have this diagram which shows us molecular shape, bond angle, and different examples of how you can think about or draw out those compounds. So if you have here methane, you're going to have a tetrahedral shape, all right, because you have 4 areas 4 areas, 1, 2, 3, 4, 4 areas of electron density. All right. And so here you have NH3. And you're going to have instead only 3 areas of electron density. All right. And you're going to have 1 area, this is non-bonding electron density. All right. So this is a non-bonding cloud. All right. And what that's going to do is really repel. All right. That's going to repel all of the other bonds much farther away. So the shape then is going to be pyramidal, like repulsion, just like with a north and south a magnet, right? 2 different magnets that repel. Okay, so bent shape. All right, so let's say you have H2O. Well, this oxygen, right, if you draw that out, your Lewis structures, you're going to have 2 lone pairs. So those are going to really push those hydrogens down. All right. And then you're going to have a structure that's called bent. And so you have 2 areas of electron density that are bonding and 2 areas of electron density that are non-bonding. All right. And so then you're going to have trigonal planar. All right. So this is another. All right. And you're going to have linear. All right. Like here, you have 2 bonding, 2 bonding, and you're going to have these non-bonding areas. And so you end up with something that is linear. And if you look at the degrees of the angles that are formed, here you have 109.5 degrees. But whenever this electron pair is going to cause the repulsion, the bond angles are going to change and get smaller, those other bonds. And same thing here. This should be even smaller, actually. I think it's like 104 or something less than that. The angles get even smaller. Or rather, and this is even smaller as far as the angles go. And then here you're just going to have a straight line because their repulsion is sort of going to cancel each other out, and this oxygen is going to go over here and this oxygen is going to fly out over here. So they're as far away from each other as they can be. All right. So up here would be closer. If they'd be angled down like this, they'd be closer. So they're repelling as far away as they possibly can with these electron pairs that aren't bonding, and it's linear. Right. So we look at a carbon atom. Carbon is our friend. We're always looking at carbon. We can see clearly a tetrahedral shape. It can have this tetrahedral where it has these 4 areas of electron density. It can have 3 areas of electron density, and it can be trigonal planar. All right. So here you don't have any non-bonding pairs. All right. And this is the shape that's formed. Or you could have linear, where you have 2 areas each of electron density. All right. So the non-bonding pairs are going to take up this space, okay? And they're going to push the other bonds closer together. So this is just sort of a written out way of what we just went over. All right. So those bonded electrons are going to be between 2 atoms, and the non-bonded electrons are not going to be restricted in the way that the bonded electrons are. All right. And they're just going to push everybody out the way, like your roommate that's taking up more space than they need to, like a non-bonded electron. Okay. So you can see here in this illustration, you've got your 2 ways of looking at this, where you've got NH3 and H2O. All right. So you have this lone pair up here, You see how it's pushing. Oh, see the degrees, it's 107. That's what the angles have changed to. It's gotten smaller than 109.5 because this lone pair is not causing this equal spread. It's causing an unequal spread because it is repelling the others away more so than the others are. Okay. And here you have this bent structure because you have this lone pair of electrons here and this lone pair of electrons here, pushing these bonds as far away from each other as they can, and you end up with this bent structure where you have an even smaller angle between those bonds. So you're also going to have to think about the molecular shape of larger molecules. Okay, so you might have multiple carbons, right? Like you have right here in this example. All right. So using that valence shell example that we were talking about, the shape around any single atom that is bonded to at least two other atoms can be determined. All right. So if you look at one or more of the atoms of interest in the molecule, you can determine the shape around those atoms. All right. So if we look at this carbon, we see that there are 4 areas of electron density, and we have a tetrahedral shape. And around this carbon, it's the same. All right. You have 4 areas of electron density, tetrahedral. And here with this oxygen, it's going to be bent. All right, so just break it down and look at your central atoms one at a time. All right, so oxygen has those 2 lone pairs, so that's still going to be bent. Okay. All right, and then we're going to get into electronegativity last. So we're almost through with chapter 3. I know chapter 3 goes super quick. So let's work some of these problems. Section 3.6. All right, we've got a carbon. All right, so let's see what we've got here. We've got the central atom, that's carbon. All right, so what are we going to do? So if we have a wedge line, all right, we want to indicate whether the orange colored atoms are in front, behind, or in plane. So how do we figure that out? If it's a wedge, then what? That's right. It's behind. And if it's a dash, like, or I mean, I'm saying this correctly. If this is a dashed, then this is behind. And if we have the wedge, then that is what? In front. I'm saying it wrong. All right. So this is in front, this is behind. These standard bonds are in the plane of the book. All right. In the 2D plane. Okay. So B, let's see if I can say this right this time. If we have the dashes, we have, no, it's almost like it's opposite day. It's behind. All right, this bond is going behind the page, and this wedge, all right, that's in front. All right, so let's do, you can look at 3.46 ahead of time and make sure that you get it right in class. All right, 3.47, determine the shape around the central carbon. All right, so determine the shape around the central carbon. So what we can say about that is for carbon, that's this one, we have how many areas of electron density? All right, if I erase a little bit around here, you can see that we have 1, 2, 3, 4. 4. So if we have 4, bonding areas of electron density. So that is tetra, 4 tetrahedral. All right. Easy as pie. Just think about that chart, study it well, and understand how to name those shapes by knowing the areas of electron density. Okay, so 3.49. Let's see, I'm gonna do this one. All right. So let's see what we have to do here. Determine the shape around the orange colored atom or atoms in each of the following Lewis structures. A, dimethylamine, an insect pheromone. All right, so let's see. What are we gonna do? All right. So if you want to know the shape around the orange colored atom or atoms, you locate those, you have that nitrogen and that carbon, and let's figure it out based on the Lewis structure. So the nitrogen has 1, 2, 3 bonding, 3 bonding pairs, 3 bonding pairs, and 1 non-bonding. All right, so that is going to be pyramidal. It's like a pyramid. Those lone electrons are going to push all of the other bonds away and decrease the angles between them, right? In carbon, we've seen this example. We have 1, 2, 3, 4 areas of electron density, all bonding. So that is tetrahedral. All right. So that gets us to electronegativity. So let's talk about that a little bit. Electronegativity. Okay, so when we were talking about the relationships between atoms and their electrons in their valence shell, I told you that there was some certain degree of attraction for those bonding electrons. And that bonding, that it's not really a want, but for the sake of understanding, if you're going to personify these atoms, it's the want, like how much do they really want those electrons? And that word that defines that is electronegativity. That's the word that describes that, all right, for covalent bonds. So you can always remember, and it's repeated several times in this PowerPoint. If you go over the PowerPoints a lot, you're going to do well on the test. The element, the greatest electronegativity is fluorine, all right? So as you get closer to fluorine on the periodic table, you have more electronegativity. So the periodic table is really like a map for electronegativity. If you know that going from the bottom to the top, electronegativity increases, and from left to right, electronegativity increases. So where do you end up right here? Fluorine. I told you how much fluorine really wants to just get that one more electron. It really wants it really bad. So it has a really high electronegativity. You see 4.0 value of electronegativity. That's the highest value. You can see everybody else in relation to that. So you see 0.7 to 1. You see 1 to 1.5 to 2 to 2.5, 3, 3.5 across the periodic table. So if you think of the periodic table and even where metals and non-metals are, you can think of electronegative relationships, all right? And that's important when you're trying to understand the electronegative relationships between compounds, or atoms in a compound rather. So when 2 different atoms in a covalent bond in a covalent compound are sharing electrons in an unequal way, meaning that an electron might spend more time closer to one element, one atom of one element compared to the other atom in that compound, that's called a polar covalent bond. So we're still in covalent, but that's a polar covalent. All right. So the sharing indicates the polarity. All right. And if they're shared equally, that's nonpolar. Nonpolar. So like polar bears, you could say polar bears are they're sort of unequally sharing the fish that they eat. All right, so they fight with each other. Angry polar bears. All right, so polar, covalent, they're not sharing equally. Non-polar, not polar bears like penguins, they're sharing equally. However you want to think of it. I just made that up just now, but if somebody uses that example, it may help them to remember that on the test. So, or forever, which is even more important. So, uneven sharing of electrons in a polar bond can be showed by the Greek letter delta. All right. It's not the easiest letter to draw, but you can get some practice. All right. So it can also be noted by a dipole arrow. So these things are going to indicate partial negative and positive charges because of the way those electrons are shared. So if you look right here, you have hydrogen bound to hydrogen. All right, they're happy. Now they're both sharing and they both have two valence outer electrons. All right, so they're happy about that. Okay, so these hydrogens are happy. That's equal sharing. All right, like penguins. That's nonpolar. They're sharing. All right, equal sharing. So you don't indicate any charges here. All right, so you don't use this letter and you don't use the dipole arrow. But here with chlorine and hydrogen, chlorine is a lot more electronegative than hydrogen, right? So what are the numbers? What are the electronegativity numbers for those? Can't quite recall. Look at your electronegativity table. What does it say? It says that chlorine is, I think, okay, 3.1 or 3.0, and hydrogen is 2.1. So there's a big difference between the electronegativities between these atoms, all right? 0.9, and anywhere from 0.4 to 0.5 to 1.8 as a difference of electronegativity between two atoms means that there's going to be some polarity there. It's going to be polar, all right? So there's going to be some positive, some partial negative charge going on, all right? So whenever you have a difference that falls into this range, you've got to realize that. So you can know that by looking at the electronegativity of these two atoms, or just knowing where those elements are located on the periodic table. How far away from each other are they, as an indication of polarity, because the table is a map of electronegativity and therefore polarity. Okay, so when you have this, you see that there is this dipole arrow also pointing towards chlorine. So this means that more of the electronegativity, more of the charge, the electron spending more time with chlorine than it is close to hydrogen. So that hydrogen then is going to have a partial positive charge. All right. So you can use the dipole area that way. So you almost make it like a positive close to the hydrogen, or you can use also the deltas with the positive and the negative. So a covalent bond that doesn't share equally is going to have those two distinct poles or ends. All right. So this is just written out everything that I just said. All right. These bonds are polar. All right. So one that is nonpolar, sharing equally, right? So once again, you can just look at the periodic table or electronegativity, the difference between the electronegativities to understand if there's what the polarity is going to be like. You can use it as a predictor. And so here shows you, all right, this is be like if we have two hydrogens sharing equally, all right, that's nonpolar, all right, so it has 0. The difference between the electronegativities of hydrogen, if hydrogen we have 2.1 minus 2.1, we get 0, right? And if we have unequal sharing like hydrogen and chlorine, all right, this is where you would draw your delta or your dipole arrow, and that's polar. It's covalent. It's a polar covalent bond. So that's different from ionic, all right? Beyond this point, if the difference is that big between the electronegativities of the elements in the compound, the atoms of the element in the compound, it's going to be an ionic bond. So if you think sodium chloride, all right, the difference is so much that instead of saying shared, we say electrons transferred, all right, lost and gained. That's ionic. All right. And so this is just everything that I just told you, basically. So it just talks about what an ionic compound is. If that difference in electronegativity is so great that it's not considered shared. All right. And so all you have to do is understand whether they're metals or non-metals to understand whether bonds are going to be ionic or covalent, or understand what their polarity is going to be like. One thing that you can remember about electronegativity is where it is in respect to fluorine, all right? Because it is the most electronegative at all, and you understand that is because it's at the top of the periodic table and it's to the far right, all right? So think, if you draw this, this is how electronegativity increases up, and it increases to the right. So look at that illustration and you'll understand. You can draw that on your periodic table that you'll have with you in your test. All right. So the farther apart they are, you're going to have a greater electronegativity difference. You're going to have more polarity, all right, in that compound, in that bond between those atoms. All right. So one of the major exceptions are carbon and hydrogen. Even though they would be nonpolar or nonpolar, even though they might seem like, because they're far away from each other, that they might be polar. They don't have electronegativity values that are that different from each other. Okay. So here are some other ways for you to look at this. A polar molecule has an uneven distribution of those electrons. That's what's happening. And a nonpolar molecule has an even distribution of the electrons over the entire molecule. They're equally sharing for the equal amount of time. They're both spending just as much time with that electron that they're sharing. That's what that means. Okay. So whenever a molecule has only two atoms connected by a covalent bond, the polarity is going to be determined by the polarity of that one bond. But whenever you have three or more atoms in all these bonds, several bonds, you have to consider all of these electronegativity relationships and polarities in order to understand the total polarity. And you have to consider the shape of the molecule, which is why we already went over the three-dimensional shapes of those compounds. Okay. So for examples, if you have carbon dioxide and water, all right, so if you look at the electronegativity values for carbon and oxygen, you'll know, oops, that doesn't make sense. Silly. You'll know that there is definitely some polarity between these bonds, all right? And you have these two areas of electron density. And you know that with oxygen, you have this one bonded and two bonded areas of electron density and these two non-bonded areas of electron density. And you definitely have some polarity there. All right. And so you can also see here with the dipole arrows what's happening. All right. So if you also draw an arrow for water for the total direction of the polarity for that bent molecule, as we talked about this already, you'll see that there's definitely a polar relationship. But here you see these oxygens, they're pulling apart in this way, as far away from each other as they can possibly be. And so this is going to be a linear molecule. And even though you have some polarity to this, for both of these bonds, it's going to cancel out and it's going to be nonpolar. So carbon dioxide is going to be nonpolar, while water is going to be polar. It's going to have this shape. It's going to be polar. All right. So that's why this is different whenever you have these compounds. You have to account for the electronegativity for the entire compound and the shape of the molecule. All right. So that's another way that you have to keep in mind what the polarity is going to be. All right. And so this basically just explains everything that I just said. All right. So you can read that before class and make sure you understand that. So it's basically just a little log of everything that I just said. So let's work some of these problems. 3.51. We're almost done. All right. I lumped it all into one video and I tried to keep it concise for you so that you would definitely watch it. For each of the following molecules, draw the Lewis structure, label each polar covalent bond with a dipole moment arrow, and determine if the molecules are polar or nonpolar and draw the dipole moment. Okay, let's see. So let's do HCl, hydrochloric acid. Okay. So if we draw out our Lewis structure, we have 1, 2, 3, 4, 5, 6, 7, and we have hydrogen here. We draw our bond. We have all of these lone pairs here, but we only have 2 atoms in this element. So the polarity is going to be determined by the pool of the atoms here. And you know that chlorine is much more electronegative. So you're going to have this type of polarity. All right. So you have a definite polar molecule here. All right. And this is, of course, covalent. You got a nonmetal and a nonmetal. All right. So B. All right. So what do we have? So carbon is going to be the central atom. Sorry. Carbon is going to be the central atom. So we have carbon's going to be bound to oxygen this way. And draw this out however you need. And you know that we have 2.5 and 2.5, and we have 3.5 for the electronegativities here. So here, this is nonpolar between these 2 molecules, but this is actually going to be polar. All right. So one bond has polarity. But the other one doesn't. But still, it's going to be polar covalent overall. All right. And you have nonmetal and a nonmetal. All right. And I'm going to do C, and you can do D on your own. All right. So, all right. So we're going to have sulfur in the middle. It's going to be bound to hydrogen this way. So we know what 2.5 is electronegativity, and we have a much lower negativity for hydrogen. Now, if this was between carbon and hydrogen, I know we would say that that is nonpolar, but for reasons defined in your textbook, the relationship between sulfur and hydrogen is going to be polar, even though sulfur and carbon are going to have a similar electronegativity. All right. So just take my word for it and don't get confused. But you can work D on your own. All right. And you can look in your textbook for the answer also. And if you can't get it, we'll get it in class. All right. Tell me to do that one. then if you don't think you got the right answer, or come to my office and we'll work it out. All right, so what is the real shape that we have here then? So we have these electrons that are going to be pushing these bonds away, really, these non-bonding electrons, okay? And so you're going to have, if you have your whole molecule polarity here, knowing that sulfur is going to be considered more electronegative, that way you know that you've got a polar molecule. All right. Similar to the way it worked with water, kind of. All right. So you've definitely got a polar molecule here. All right. Don't let that confuse you. I'll go ahead and work D. All right. And that's gonna be it. That's gonna be it. All right. Thank you.